Dear students, welcome to the lecture on coordination chemistry, module 1. Myself, Arun Prakash. So I will teach you the topic, particularly the crystal field stabilization, and this is a follow lecture in the lecture series, chemistry lecture series, and we will discuss about the crystal field stabilization energy. So this is one of the important concepts. So now you have understand about the crystal field theory and the crystal field splitting for tetrahedral and octahedral complex. Okay, so now we need to understand about the crystal field stabilization energy. Usually, this they will ask in a question like how will you calculate the crystal field stabilization energy for a complex which is having a low spin situation or high spin situation based on the weak and strong field based on the strength of the ligand. So what do you mean by crystal field stabilization energy? So it is nothing but the energy difference between the distribution of electrons in a particular crystal field, and that for all the electrons in the hypothetical spherical or uniform field level. So with respect to the barycenter that you know is called crystal field stabilization energy. So you will take the barycenter as the relative or mean position from which you will calculate this one. So can we put it very simple, like you can calculate the crystal field stabilization energy for any complex. For instance, we are going to calculate for the octahedral complex, particularly D1 to D3 system. So the crystal field splitting energy will be delta O, that you know, the crystal field splitting gap delta O on octahedral complex. So how will you calculate this CFSE for this octahedral complex? Calculate the number of electrons in T2G. Just count and then time it by minus 0.4. As you know that this is the value. Do you remember the CFT diagram? So there we put minus 0.4 for octahedral complex at the bottom, T2G, and the barycenter, that gap. And for the above the barycenter, you will have plus 0.6, which is pushed up, right? So you will put number of electrons in EG times it by 0.6. This I hope you can correlate and link. Okay, so now for this D1 to D3, whether it is weak field or strong field, it doesn't affect that much, but still the gap will be changing. For a strong field, this gap will be T2G and EG gap will be more, and weak field case it will be small. D1 means only one electron, so just T2G1. Even in the weak field case also T2G1. So similarly, the second electron will go to the T2G2 and T2G2, but the gap is small. Again, I'm repeating. And the third one, third orbital T2G3 and T2G3. Only the difference is larger the gap for strong field, smaller the gap for weak field, whether it is D1, D2, or D3. Now, what do you need to do to calculate CFSE? Just count the number of electrons in T2G. For D1, how many? 1. So 1 into, what is the value? 0.4, 0.4 delta. If it is 2 for D2, 2 into 0.4, 0.8. 3 for D3, 3 into 0.4, 1.2 delta. That's simple. So we have read this hexacotitanium complex, that is D1 system. We have calculated the optical property now. So that one, how many electron? D1 means only one electron. So what is the crystal field stabilization energy? 1 into 0.4, 0.4 delta O. Now we know that delta O, this energy for this one splitting the gap, that energy will be 243 kilojoule per mole. So when you multiply this uh, uh, 0.4 with this delta O value, you will get 97 kilojoule per mole. Since this value is less than 100 or less, small compared to the other cases, this complex is more stable. Now you understand now? From the CFSE, you can also determine the stability of the complex. That is what I want to mention here. And now let's see how the electron fill the uh, orbitals T2G and EG in the case of D1 to D10 system. D1 to D3 is very simple. They are 3 electrons now. So they will singly occupy the T2G orbitals. But in the case of D4 to D7 only, you will have this situation. because metal ions with D4 to D7 electron configuration can be either high spin or low spin. So now we have to, high spin means more unpaired electron. Low spin means less number of unpaired electrons. Just keep it simple. Now let's move on to the D4 system. Chromium Cr2 and Mn 3 plus. Here you are having 4 electrons. Low spin means, which means the gap is more, strong field gap, like cyanide. So the gap is more. So that the fourth electron cannot jump to Eg. Where it will go? T2G1. So how many number of unpaired electrons you are having? 2. Whereas in the case of a weak field ligand, the gap is small. Gap small means you can jump easily to the Eg. So you will get 4 unpaired electrons. So in the case of weak field ligand complex like fluoride, COF6, or a CRF6 you can say. So in that case, you will be having 4 unpaired electrons. Whereas in CrCN6, you will be having how many unpaired electrons? 2 unpaired electrons. So this is how the situation changes with low spin and high spin complexes. Similarly, for D5 system, all the 5 electrons are singly occupied and the orbitals are half filled. In the case of Mn2 or iron 3 plus D5 system, in the case of weak field ligand. In the case of strong field ligand, it is a low spin situation. So the pairing will happen. Fourth electron will not go to Eg. Where it will go? It is not going to Eg, it is going to T2G1. Fifth electron is going to T2G2. So the unpaired electron is 1. Look at here. In the strong field case, the gap is more. Only you are getting 1 unpaired electron. Here you are getting 5 unpaired electron. Similarly, for D10 system also, you can see the 5 electrons, 5 d orbitals are completely filled. Whereas here, how it will happen? First electron will go to T2G1, second, third, and fourth will not go to up. Where it will go? Fourth, fifth, and sixth. First T2G will be completely filled because the gap is more. Then only the last electron it will go up. That's why you are having low spin situation for this case, for the D7 case. Whereas here this filling will not happen. Here how will it happen? First electron will occupy T2G1, second T2G2, third T2G3, fourth electron will go to, pairing will not come. Here it will not come. It will go to Eg1, Eg2. So now it is half filled now. Then the sixth electron will come to T2G1 and seventh electron will come to T2G2. This is how the situation happens for both low spin and high spin. Just remember this one. So for these 4 system, where is D4? This one. For high spin complex, that is this 4, 4 into, you can calculate the value. So that is 0.6 delta O, and CFSE here 1.6, only 2. So you can calculate the unpaired electron and you can put it in the number. So just remember larger delta O low spin complex, smaller delta O high spin complex. In that way, you can also, this table is very useful. Like you have the D1 to D10 system, and until D3, it will be the third electron will be entering T2G itself. But whereas for D4, you got the weak field ligand and strong field ligand. For instance, D4, the fourth electron will go to Ug, whereas here pairing will happen. So T2G4. So that since the number of unpaired electrons are different for both D4 system, that is weak field and strong field. How many unpaired electron here? 4. Unpaired electron 4. Here 2. So obviously their CFSE value will be different. This is the same for all the situations. Okay. And now in your examination, they will ask you to write like what is strong field or weak field like and explain a situation with a complex. Take one, give one example like that. They will ask either in 8-mark question or a 4-mark. One option will be asked. So how you will write that question? Like for example, you can take the D6 system cobalt CO3. Choose one weak field ligand, I mean weak ligand, other one strong ligand. Fluoride is the weak ligand. Cyanide is the strong ligand. So you can choose an octahedral complex, 6 coordination number, COF6 3 minus, COCN6 3 minus. So now you can write this one. So how this electrons will be filled? The first D6 na 6 electron. So the gap is small. Why? Because it is a weak field ligand. So that first electron will occupy T2G1, second, third. Now the fourth electron will jump to the Eg1. Fifth electron will jump to the Eg2. Then only the sixth electron will move to T2G1. So now you will have 4 unpaired electrons. So number of unpaired electrons 4. So this is a high spin complex. More the number of unpaired electrons, this high spin. Whereas in the case of COCN6 minus, look at the gap, it is more. So when you draw this diagram, for weak field you have to put small gap, and for strong field you have to put a larger delta O value. So the first electron will occupy T2G1, second T2G2, third T2G3, fourth it will not jump to Eg1, it will go to T2G1, then fifth T2G2, sixth T2G3. Okay, we got it right. So how many number of unpaired electrons are there? 0. So this complex is not magnetic. This complex is magnetic. It is having 4 unpaired electrons, so it is paramagnetic. So like that you can also determine. Suppose you are not, you can either you can write the cobalt system, D6 system or D5 system. So I am giving 2 examples, you can follow any one. So FeCN6 3 minus. So here the number of unpaired electrons, so the number D5 means 5 electrons. So the number of unpaired electrons will be 1. Why? Because the larger delta O, why? Cyanide is a strong field ligand. So the first, second, third will be singly occupied. Fourth electron will come here, fifth electron will come here. So you get one unpaired electron. Whereas in the case of hexa-aquo ion complex, this is also an octahedral complex. So you remember for any strong field or weak field case, take octahedra and either choose D6 situation or D5. So that will be easy for you to write. And here you can write the uh, uh, first electron, second electron, third electron. Fourth will, since the gap is small compared to cyanide, fourth will go here, fifth will go. Obviously, how many unpaired electrons? 5 unpaired electrons. So obviously, high spin, and this will be low spin. Are you able to follow? Similarly, you can calculate the magnetic moment for this complex. Just count the number of unpaired electrons. So there is a formula mu S is equal to square root of n into n plus 2, where n is the number of unpaired electrons in the complex. That we will see. So this is the detailed calculation for the crystal field stabilization energy. This is the formula, number of electrons in T2G into minus zero point 0.4 delta O, that you know, number of electrons in Eg times 0.6 delta O. Uh, so they will ask you to calculate the crystal field stabilization energy for COF6 3 minus. So cobalt will be in +3 oxidation state. Am I right? And fluoride is a weak field ligand. These are the two things you have to remember when you see a complex. And they will give you an option like this. What is the answer? So the answer will be C minus zero point 0.4 delta O. How to calculate that? You know that 3D7 4s2. This configuration you will, because cobalt is a D7 system. So you will write this one. But it is in +3 oxidation state. So you have to write this in hybridized electronic configuration for the hybridization state. For example, CO3 plus you have to write. It is in oxidation state 3 plus now. So remove 3 electrons, 1 from D and 2 from S. So you will get 3D6, 4S0. So where these 6 electrons will go, as I said, 4 electrons will occupy T2G like before, and 2 electrons will occupy Eg. Why? It is a weak field ligand. So whenever you are seeing some electron in Eg, it means it's jumping from T2G to Eg. Why? Because the gap is small. Why? Because it is a weak field ligand. These things you should remember. So calculate the number of electrons in T2G, 4. 4 into minus zero point 0.4 delta O plus 2 into 0.6 delta O. So you will get minus 1.6 delta O plus 1.2 delta O. That will be minus zero point 0.4 delta O. Are you able to follow? So in that way, you can calculate the crystal field stabilization energy for this particular complex, cobalt complex, hexafluorocobalt. And now, pairing energy. This is an important concept. There is only two situations. I will explain that one. But what do you mean by pairing energy? So it is the energy that is required to force an electron to pair with another electron in the same orbital with same energy. It's called pairing. Whatever the energy required, you need to supply that energy for an electron to occupy the same electron, same orbital where another electron is present. Like pairing, that is called pairing. What will happen if an orbital, okay, one orbital T2G1, let's consider like that, D4 system. So three electrons will singly occupy. Fourth electron has to occupy the T2G1 now. So which means you have to give some extra energy for that fourth electron to occupy the T2G1. Why? Because there is already one electron. So due to electron-electron repulsion, why? The electron is negatively charged now. So Coulombic repulsion arising out of forces between these two electrons trying to occupy the same orbital. This is the first situation. So once it is trying to occupy the same orbital, what will happen? The loss of exchange energy will occur. Why? To cancel out the spins. For example, one electron will be having, both are entering the same, means we're having parallel spin. Na? So excess energy is needed to change that parallel spin into anti-parallel. That's why, do you remember, we are putting an arrow like one pointing upward, other pointing downward. Na? So anti-parallel. So that situation happens. Okay, there are only two possibilities. Compare the crystal field octahedral, for example, octahedral complex, delta O, that energy gap now. Whether it is greater, pairing energy is greater than or lesser than that energy. Let's see that one. Pairing, and first let's consider P, pairing energy is greater than delta O. What does that mean? Which means you have to, it requires higher energy, so pairing will not happen. So look at here, for D4 system, T2G is having 3, fourth electron is not pairing. Why? Because you need higher pairing energy, so the fourth electron will go to upper. What will be the expected outcome? Since pairing is not happening and more higher pairing energy is required for pairing to happen, so that all the four electrons will be unpaired. So high spin complex situation and highly magnetic. You remember that one. This is known as weak field or high spin situation. That's what I told. And then if the pairing energy is small, only small energy is required. As a result, for example, that fourth electron jumping to EG na, only small pairing energy is required na. So that fourth electron will go to T2G1 itself. So T2G orbital will be, first orbital will be having two electrons and the second and third T2G orbitals having single electrons. So that two unpaired electrons will be present and one paired electron will be present. So this leads to strong, it is paired now. Paired up means low spin situation. When it will happen? Pairing will happen when strong field ligand is present. So let's take this example, hexa-aquo ion complex D6 system, hexacyanide. So among aqua and cyanide, which is the strong field ligand? So obviously cyanide. So that it is having higher pairing energy, um, so which means 32,200, and this is having 9,350, and the delta O splitting energies are also 1900, 150, and this is how the situation will happen. Pairing energy will be greater than delta O for the first case, and pairing energy will be lesser than delta O. And also you can calculate the magnetic moment. For example, uh, in this case, 4 unpaired electrons are present. So square root of n into n plus 2, n is the number of unpaired electrons. In that way, you can calculate the magnetic moment. I will show you the next one, the formula. So the magnetic properties of metal complexes. So due to magnetism, we know that it's caused by moving charge particles. That is what Faraday said in 1830s. Whatever the particles moving, the moving particles can generate current, can be the current of electrons through an electric wire. Like when the electrons are moving from one end of the wire to the other wire, contributes to current. on the movement of charged particles, protons or electrons within an atom. These charged particles move much like a planets in a solar system, which means like a elliptical orbits they will be running. So the nucleus spin on its own, we know that. So a magnetic field will be generated, which will be weaker magnetic field. When electrons are revolving around that nucleus, means that will cause a weak magnetic field. But electrons spin around their own axis, now that is causing a significant magnetic field. So spinning electron generate the bulk of the magnetism in an atom. Just remember this one. So within each orbit, electrons will opposite spins can pair together, resulting in no net magnetic field. So whenever as an orbital, both electrons are occupying the same orbital also, it will nullify. Same orbit also opposite charge will cancel out. So only unpaired electrons will contribute to magnetic moment. The formula to calculate the magnetic moment is nu s is equal to square root of n into n plus 2. For example, in D1 system, you are having one unpaired electron. So n will be 1, 1 into 1 plus 2. So 1 into 3 will be square root of 3, which will be 1.794 magneton. So in that way also you can do, and also you can calculate with this formula square root of 4s into s plus 1. So s is equal to